Let us look at the chain rule for functions of several variables. So for example, here I have a function f which depends on two, x and y. And if I write z equals f of x and y, then I get a surface. But now I assume that x and y themselves are functions again. So x is a function g of t, y is a function h of t. Then we can apply a chain rule and write the derivative of z of t as dz by dt is the partial derivative of z by x times the partial derivative of x by t plus dz by dy, dy by dt. That's a rather simple formula, so let's apply it to an example. Here's the example. So the function of x and y is x squared y cubed, but now x is given as a cosine of t and y of t is given as e to the minus t. Now I'm interested to find dz by dt at the time t is equal to pi. You remember from derivatives earlier that we first compute the general derivative function and then later we sub in the value t is equal to pi. So let's jump right in, move back one page, look at the formula again. Ta-da, here it is. So we have to differentiate z by x and then x by t and plus dz by dy, dy by dt. All right, let's jump right in. So dz by dx, I differentiate the function by x and keeping y a constant. So this is 2x y cubed. Then dx by dt, so I just differentiate cosine, which is minus sine. And then plus dz by dy, so again back to the function f, we got a y cubed, so this gives a 3x squared y squared, keeping x a constant now. And then dy by dt, this is minus e to the minus t. Now I would like to write this as a general function in t, so then replacing x and y wherever I can. So then this is 2 times x, and x is cosine. Y cubed, this would be e to the minus 3t. And then we keep the minus sign, t. And here we get a minus sign, so minus 3, x would be cosine of t all squared. Y would be e to the minus 2t, and then we keep an e to the minus t from the bracket. And now we can sub in the time value. T is equal to pi. And you can notice that the sign at pi is equal to 0, which makes the first term disappear, but we keep the last term, so minus 3. Cosine at pi is minus 1, and square is plus 1. And then we have e to the minus 3 times pi. And that's the result. Let's try for an interpretation. So what did we do? We computed the rate of change dz by dt, but what rate of change did we compute? Let me try to plot this. This is a rather complicated graph to plot, but I give it a try. So z equals x squared y cubed is a surface. So let's try to plot this surface. In x we have a parabola like this, and in y we have a cubic which goes maybe up like this, and then we have to piece it together into a surface, and this is one way you can do this. So it looks a little bit like a chair. And then on this surface we walk in x and y as a function of time, so this makes a path on the surface. In x we oscillate with a cosine, and in y we decrease. So what it looks like will be something like this. This will be a path. We are moving on the surface going down to 0. Cool, isn't it? However, I must admit I was not able to produce this picture on a computer. I'm just not skilled enough. So if one of you is interested to create this picture with a graphical program, please send it to me at thillen@ualberta.ca. Now dz by dt is a rate of change, and it's the rate of change in z, so the height. So dz by dt tells us how quickly we descend as we follow the red path. Actually, this example here is so simple that we can just directly compute the result as well. we can simply substitute x here and y there. And so then we get z of t equals cosine of t square e to the minus 3t. And then the derivative is just a product rule. So dz by dt would then be differentiating the cosine t square. So we get 2 cos t, inner derivative is minus sine, keeping the e to the minus 3t, and then plus differentiating the exponential, keeping the cosine t square times minus 3 e to the minus 3t. And then if we sub in, t is equal to pi, then again the sine term disappears, but the other term remains, and this is a minus 3 e to the minus 3 pi. Same result as before. Here's another example where we apply this to the ideal gas law. So the ideal gas law is pressure times volume is equal to 8.31 times temperature. So the question is now, what is the rate of change of the pressure when we know that the temperature is 300 Kelvin and is increasing at a rate of 0.1 Kelvin per second, and the volume is 100 liters, increasing at a rate of 0.2 liters per second. We are interested in the rate of change of the pressure. So what we need is we need P equals something, but then ultimately we want to have dP by dt equals something, because that's the rate of change. Here's the problem again, so then I can solve it for P, right? So then P would be 8.31 T over V. But now T and V are changing in time. So the whole thing then would be a new function which depends on T, which depends on time, and V, which depends on time. It's exactly a chain rule situation where you have more than one variable depending on T. So we can use our wonderful chain rule. So then dP by dt would be dF by dt, dt by d little t plus dF dV, dV dt. Okay, so then let's just do that. So then F differentiating by capital T, this what just gives an 8.31 divided by V. And then the dt by d little t would then remain just dt by d little t. And then plus dF by dV, so then we get a minus 8.31 times t divided by v square. And I just keep the dV by dt term unchanged. Now I look at the problem. So what does the problem give me? So look, in the first one we have the temperature of 300 Kelvin. So we're looking at a situation where T is 300, and at that instant it's changing at a rate of 0.1 Kelvin per second. So this means dt by d little t is 0.1. And so these are values already which we can then sub in here and here. And then volume is 100 liters at this instant, okay? And then the volume change is given to be 0.2. So this we can sub in there, there, and there. All right. Then we can sub in all the numbers. 8.31 we keep. The volume is 100. The temperature change is 0.1. And the other term has a minus 8.31 here. The temperature is 300. The denominator volume square is 100 square. And then the volume change is 0.2. Great. Now it's a matter of calculator. Subbing in the numbers, we get minus 0.04155. The pressure is decreasing at a rate of 0.04155 kilopascal per second. Okay, this is a little typo like that.